carbon dioxide has roughly the same mass as water molecule. A carbon dioxide molecule has roughly the same mass as a water. Actually, that's not true. It has a greater mass.
What? Get out.
Yeah.
No.
Okay.
Whale?
Well, just add them up.
Oh.
These are roughly 16. That's
16,
roughly
right.
12.
Yeah, 16 plus 12, that's what, 28.
Yeah, but you got to have two 16s.
Oh, right.
Okay.
Oh, so it's 32 plus
And
12.
yet it's a
Oh.
gas at room temperature and pressure, where water is a liquid.
Wow.
And water is a liquid because of this interparticle attraction. The molecules are pulling closer together, pulling more tightly together because of these polar or dipole-dipole attractions.
Dipoles, right.
So that's why water is a liquid at room temperature and pressure, but carbon dioxide is a gas at room temperature and pressure.
Yep.
Okay, even though this weighs more, you would think that if it weighs more, it can't move around as fast. Does that make sense? Momentum makes sense to you guys?
Yeah.
Okay.
Like a
Bigger
car.
things are harder to move around. Okay. If you want to look at two molecules that actually weigh about the same, you can look at methane and water. They're about the same mass, and yet this is a gas, that's a liquid at room temperature and pressure, because this is nonpolar and this is polar. These molecules pull on each other much more strongly because of this dipole-dipole attraction. Methane doesn't pull much on the next methane because of it has very weak attractions. Okay, by comparison anyway.
Yeah.
All right? So that's a dipole-dipole. Now, let's talk about something that's a permanent dipole. And the attractions between molecules that have permanent dipoles. Now let's look at what are called temporary dipoles. Temporary dipoles. And this is why all molecules have stickiness. All molecules have stickiness, whether they are permanent dipoles or not. Yes?
And dipoles are only for covalent bonds?
No.
Let's be honest with this stuff.
No, it's not. But let's,
No, it's still
because it could apply to, for instance, noble gases, which are single atoms, no covalent bonding at all.
Right.
So-
right.
There's a certain amount of this sort of attraction going on, even when you have other kinds of things, but they're just overwhelmed. Like there can be a temporary dipole with ionic bonding, but it's so weak compared to the ionic attractions themselves, it's like negligible. You just kind of ignore it. That makes sense?
Yeah.
But are we just going to be ones with covalent then? Or are we still going to...
And we're going to be dealing with any kind of particle attraction in this unit. Okay, we're trying to look at how particle attractions affect the physical state of a substance. That's what we're dealing with, what we're getting to eventually here, okay? After I kind of explain some of these things. All right? All right. So let's look at a molecule that is nonpolar.
That's a good circle.
Not really. It's kind of sloppy.
So you connected it to. It's a good sloppy circle.
Okay.
Whoa.
There we go.
Woo! Woo! Oh, South Park.
No, we don't want to do that. Okay.
Come on, man.
All right. So here are two molecules. Okay. In every molecule, of course, the electrons are moving at nearly the speed of light. Now these are nonpolar. I haven't put any polar things on here. Okay. So they're not permanent dipoles. But the electrons are moving at randomly at nearly the speed of light. Okay. Statistically, then, there are times, and in fact, at any given time, half the time at least, well, even more than that, more than half the time, the electrons have to be unevenly distributed. If you understand a little bit more about statistics and that sort of thing, random movements, and that's way beyond, again, that's kind of, you can do that mathematically. We're not going to try and deal with it in here, but if you think about it, if you have little cars, you know those little cars, you don't even,
That's not Hot Wheels.
well, years ago, there used to be these little cars.
Fisher Price.
They weren't remote controlled, but you would turn them on, and they would run till they ran into something, and they would turn and run till they ran into something.
Oh,
Are you talking about the things that you back up?
well, that's not normal.
No, these are actually motorized cars. Now listen. So if you think about electrons as kind of little motorized robots or cars that run until they run into something and they turn and go somewhere else, okay? And you just put them down in the middle of a circle and let them go, okay? They're not going to be evenly spaced out all the time.
No, they're going to be clumped together sometimes.
Sometimes you're going to have more electrons on one side than the other.
Right.
In fact, statistically, you have them clumped on one side more often than you do that's evenly spaced. In fact, evenly spaced is an unusual state.
Yeah.
Wow.
Okay? All right. So if they're unevenly spaced,
Tom, you paying attention, brother?
we have way more electrons over on this side of the electron cloud than we have on this side.
Why are there none in the middle? Is it just
They don't want to be in the middle.
Well, I didn't know if like
All right. So by using that same idea behind a permanent dipole, where the electrons are grouped more on one side of the molecule than another all the time, creating polarity. Okay? The reason that a water molecule is polar is because the electrons tend to spend more of the time on the side of that molecule, that bent molecule, on the side of the molecule with the oxygen, because it's more electronegative than hydrogen. Okay? Well, this then creates a temporary dipole. This is a temporary condition, a temporary dipole. So temporarily, for a brief period of time,
Brief.
this is partially negative on this side,
Oh,
and this is partially positive on this side.
dipole.
Okay, yeah, we have a temporary dipole.
Oh.
All right? If this molecule happens to come into the same vicinity as this molecule, and if this molecule also has that same condition where the electrons tend to be grouped more over on one side than the other, then we have a
attraction.
polar attraction that's very temporary.
Just plus on this side?
Temporary
Attraction.
dipole.
Dipole.
Which side?
I'm sorry, you're right. This side's be positive, this side's negative.
Okay.
Okay?
So, those molecules are those water?
No. Water has a permanent dipole. This is something that's not permanent.
Like, what's an example of
Carbon dioxide, like methane. Okay?
So gases? Or
Well, it happens a lot with gases, which is why the gas laws are part of this unit. So it kind of explains some of the behavior of gases.
Okay.
But it also explains some other things too. Okay? All right, so this is kind of a small molecule, kind of spherical. Okay? This temporary condition doesn't happen a lot.
Yeah.
And the smaller the molecule, the less this has a major effect. All right? Well, what if we have a really big molecule?
Oh my God, big. Go big or go home. It's off. He's raising it. Uh-oh. Get ready, folks. Here we go. Flubber.
Some really big molecules.
Holy cow.
They're jelly beans. Peanuts.
What if you make it smaller, the molecule?
The smaller the molecule, the less of an effect this actually has. Okay, let's get some really big molecules. Now you got to think through this, all right? This requires you to use
You're
the little
noggin.
movie projector in your head.
Use your noggin, man.
Use your imagination.
your noggin.
High-level chemistry is very creative. You have to use your imagination. Okay? And you're in an honors chemistry class, you're expected to use your imagination.
I have a best friend. That's in-
You run that movie in your head. Okay? What?
I have an imaginary friend.
You have an imaginary friend?
His name's Jimmy.
Well, molecules are my imaginary
Oh, his
friends.
name's Ted.
All right.
Fine.
Think about it a minute. Think about these electrons moving randomly throughout this whole structure. Okay? At any given instant in time, there are going to be groupings of electrons in different places along this molecule.
Jimmy, stop doing that.
Okay? So statistically, because of the random movement of the electrons within this structure, there are almost always going to be places that have temporary polarity along here. Right?
Right.
And therefore, because of that statistical arrangement, or that arrangement of electrons and the way they move, these molecules are more sticky than the smaller molecules are.
Oh.
Because of the temporary polarity is going to exist somewhere in here, because of that shift of electrons, they're constantly moving around. There's always places along this molecule that are going to be attracted.
Yeah.
So the bigger.
Conversely, there are also places on this molecule that are opposing. Because if you have electrons that are grouped here and here, then these are positive here, and they kind of tend to push apart. But the size of the molecule, the larger the molecule, the more stickiness you have along that surface with the next molecule.
Because of the
Yes.
certain molecules you want
Yes.
to attract.
Yes, they want to attract. Okay? You got that? Kind of makes sense?
You got it good.
So, the larger the molecule, the stickier it is with another molecule, even if it's doesn't have a permanent dipole. Permanent dipoles, though, have an even bigger effect. So the more permanent dipole you have, the stronger the attraction between molecules. The less permanent dipole you have, the less the attraction between molecules. Okay? The larger the molecule, the more attraction you have because of that temporary electron density shift.
Yeah.
Okay? So all of those factors come into it. And one other factor that affects the overall physical structure of a material has to do with how much pressure or temperature it's under. Well, temperature actually is just how fast the molecules are moving around. Temperature, by definition, to a scientist, temperature is a relative measure of the average motion of molecules. Temperature is a relative measure of the random motion of molecules, or particles, really, of any particles. The faster the particles are moving in a random fashion, the higher the temperature. The slower the molecules are moving in a random fashion, the lower the temperature. Okay? Now, random is really key, because if all the molecules are moving in the same direction, that can be a very, very low temperature, because that movement is not random. It has to be random motion. Okay? Does that make sense? Yes or no?
Sort of, kind of.
All right. Well, let's think about something like a thermometer, an old-fashioned liquid-centered thermometer.
Lord.
Yeah,
Oh, we're thinking about thermometer.
we are. I'm going to draw a thermometer.
Okay.
How's it gonna work?
Mercury. Ooh, that's good.
All right, so there's our liquid-centered thermometer. Okay. So in the center of the thermometer is the liquid that flows up the thermometer. Okay, up or down the thermometer.
Got a
All
little
right.
hot in here.
All right. If the molecules are moving faster, they're pushing apart harder. They're banging off of each other with greater force. They're banging off the insides of the glass surface more. And so they tend to push apart. Okay? The faster anything moves, you think about it, y'all did bumper cars if you went to that,
Oh, Frankie's.
yeah, Frankie's Fun Park or whatever, okay? The faster they're moving, the harder they push apart, right? They bang apart harder, don't they?
Yeah.
Okay? Molecules are kind of like those bumper cars. And the harder they hit each other, the more they push apart, the more the liquid as a whole pushes up the glass.
Did you do the bumper cars?
Huh?
Did you do the bumper cars?
I've done them in the past.
Oh, you didn't do them?
No.
Oh.
Okay. So when we all went to Mr. Gaddy's, I did not do the bumper cars. I saw you doing it though.
Yeah, I did them.
Okay. Yeah, you were dangerous out there. Okay. All right. So the more they move around, the faster they move around, the more they're going to push themselves up, the more they're going to bang off each other and push each other up. Okay? And so the liquid climbs higher. The more they slow down, the less of that effect you get, and the more the liquid sort of contracts. So temperature isn't a measure of energy. It's a measure of the average random motion of the particles in a substance. Temperature is a measure of the average random motion of the particles in a substance, or it's a relative measure. When I say relative, I mean comparative measure. It doesn't actually measure how fast those particles are moving, but it says if this substance, this material here is moving slower than this material, then this one's warmer. That's all temperature is. It's a relative measurement. Okay? Has no direct, it's not a direct measurement of any energy other than movement of molecules.